There we go. All right, I'm just dropping a link in to the testing lobby Discord server.
What do you think about like using the @everybody on Discord, or
Does that
do you know what that does?
No, I haven't used it. Does that just populate to everybody on a certain that's on a
So
certain server?
it just notifies
Just dropping
everyone.
a
Like
link
for
in
example,
to the
I
testing
naturally have a
lobby
lot of
Discord.
Discord channels muted, so I wouldn't be notified by like such things that you have posted right now, like these last two messages.
Right.
But if you type
What do you think
@everyone,
about like using the?
then it just here I can wait. Oh yeah. So doing this just like it basically like makes everyone be notified. Like this this tag @everyone. You can like do it to specific people, like if you wanted to.
All right, yeah, let me do that. So you're about to mention 30 plus people? Yes, send now.
Yeah.
Yeah, I like that. So they don't have to be just, looking over at the general.
Yeah.
Okay.
It's just a much stronger notification
Yeah, I like that.
thing.
So let me pull up those chapter 4 slides. Okay, so you said 17 through 45 was what we were missing. Okay, I'm just kind of orienting myself. So it must have been like a middle chunk.
Yep.
Okay, interesting. It's funny to just drop in without a lot of context, Okay. Alrighty, so let me do this then. What I'll do is let me back it up. Yeah, so what I'll try to do, I'll back it up to that. And then there's like, it looks like we got five viewers and 3 on Discord. So let me see. We got Ryan and William. Para Williams. We need the 3 Zacks. We need at least 3 Zacks now for a full house. Okay. Alrighty. Okay, so here's where we were at. So the way we're gonna do this is, and then just for anybody like watching this, that's on watching it after it posts as a recording. So this is the chapter 4 slides, and what I wanted to do, just Ryan, to set kind of context, is the following. This is we talked about the von Neumann architecture, right? This notion of a CPU with control unit and ALU, memory, and input and output, right? The core punchline, and that was our picture, that was our little discussion of von Neumann just before that, right? What we did in the part that there is lecture for is we talked about the notion of memory, what it was, kind of how it worked. And then the notion of the CPU, which has a control unit and an ALU. And Then we go basically through the CPU, which again has control unit, ALU, and registers. And then we were walking through, like, there's the control unit, which manages the whole flow. And then we were to the ALU. Okay. So that's kind of the setup for this part. And then the way, again, so for Ryan and the two Williams, or anybody else that happens to join on Discord, which, and by the way, anybody who's listening on YouTube, if you want to just be part of the live conversation, just jump on Discord, jump on the testing lobby server, and just jump on the voice chat, and then you can be kind of concurrent, ask questions, and kind of guide what we're doing. Okay. So the idea, the thing to me, okay, so the von Neumann architecture, this notion of, input, output, memory, CPU, control unit, that kind of a thing. Yes, that's all part of it. But to me, one of the biggest sort of takeaways of the entire von Neumann architecture is really the control unit, because it's the control unit that manages the fetch, decode, execute cycle. Okay? And we'll kind of break that down or we'll get to that part, I think, when we get to slide 45. But so the notion that the control unit is the one that's going to fetch an instruction. So I got to go out to memory to fetch it. Then I've got to decode it and make some sense out of it, right? Which is that big state machine we talked about. And then I've got to actually execute it and do what the thing needs to be done. So the critical aspects of that are inherent in the control unit is the program counter, because I've got to know where in memory I'm actually grabbing the next instruction from, right? And I'm going to increment that every time. And then an instruction register that when I grab the instruction out of memory, I've got this, I've been calling, I called it the sushi table, right? Or the little sushi counter. I pull it out and I plunk it down, and then I can slice it up and do whatever I do to it, okay? That's the instruction register. So the instruction register, the program counter points to where to grab the instruction when I'm fetching. The instruction register is the thing that holds the instruction when I pull it so that I can decode it. Then the CPU, the control unit, then, kind of drives it and executes it. Is that clear?
I think so.
Okay. If there's anything that's not clicking, definitely, kind of stop me and we'll go for clarity. Okay.
Yeah. So the control unit, that's not the total state machine, is it? Like
State machine's part of it. Yeah.
Okay, so the state machine is kind of like a child to the parent of the control unit, like if you were kind of to classify them in a hierarchy.
Yeah. Yeah. That's right. The state machine, or the state. Yeah. The state machine is part of the control unit.
Okay.
And the control unit also has other things like the program counter, the instruction register, and things like that. So then we get to the ALU, which is also the arithmetic logic unit, right? Too many syllables, so we just say ALU. ALU basically, it's math and logic. So it's the math stuff, add, subtract, things like that. We don't have a subtract, but if we did, that's where it would live. Basic logic operations, right? And or, and again, we don't have an or, we have not. We have and not. And let me see. So in the ALU, this part here, the size of values that can be handled is the word length of the computer. All that really is trying to say is that the math that the ALU does is on numbers that are the length of one location in memory. So in the LC3, every location in memory has 16 bits, right? That's one word. So that one word in memory is also the same size of what the ALU wants to do an operation. And if it's not, for whatever reason, if some value is not big enough, we notice this in the diagram, like the big diagram of the LC3, this notion of like sign extending and things like that. The sign extending is important because, you do like PC offset 9, it gives me 9 bits. I have to sign extend because I have to give 16 bits to the ALU to add stuff to. So I can't just give it partials. I've got to give it 16 bits to do the add or the and or whatever it's going to do. Okay. Um, Let me see. And then the ALU also has this like direct connection into the registers. So the general purpose registers, R0 through R7 and the LC3. That is, those are directly wired so that the ALU, you can tell the ALU, take the value in R1 and then the value in R3 and add them. And it's just like they just latch on in, boom, and then results, popping back out. Again, stop me. Then again, this is really high level, right? This is the high level pass through everything that we talked about. And this is ironic because we're talking on module 10 and we're deep into input now, right? So this is back when we were introducing the concept of input, where, you've got the keyboard, anything that's coming in, bringing stuff into the device. And we call those peripheral devices, right? Because they're out on the periphery. They're not central. So CPU, the C stands for central. These devices we call peripherals. Makes sense. And then over on the other side is the output device. And this kind of just says, this is sort of like, an output device, an input device, And so it's ignoring the idea that there are many of those, and not like von Neumann didn't know that or whatever. But in this graphic, it just is, characterizing as a device coming in, a device going out. Okay? And then the most common output is some kind of, just some kind of monitor, console. Historically, there's always been something. I'm printing to paper, I'm, dumping to a terminal. I've got this teletype going, and that's my output. There's some kind of output. Even like flashing lights can be viewed as output if that's all you've got, right? In the ancient days. Anyway, again, more peripherals. So then we collectively refer to I/O as devices that perform, well, it's I/O broadly encapsulates everything, all input, all output, but there are some devices that are both input and output, right? Like a hard drive. I can read from a hard drive, I can write to a hard drive. Stuff goes out there, stuff comes in. Network adapters, Ethernet, Wi-Fi, Bluetooth, anything else you're doing like that can be kind of in that category of I/O. This device right here, these headphones, are both a speaker coming out to this and a microphone going back in. So this device is really both an input and an output device. It's all lumped together so broadly that it doesn't even matter if it's not precise. If someone says an I/O device, they mean basically anything involved with I/O, and we just refer to it as I/O, and don't really. Then it's pretty obvious that a mouse is an input device, a keyboard is an input device. Makes sense.
Yeah, makes sense.
And then this one is just the book's view, okay, of the von Neumann architecture. So this is the one in the book. And the key here is, there's first of all, the layout's different. So it makes you kind of think about it a little bit different. There's memory, there's the MAR and the MDR that we talk about. There's output over here, and there's input over here. Processing unit, ALU. What is temp? What is temp? Temperature. I don't know what it is. Temporary. I'm serious. I'm totally blanking on that. I don't know. And then there's the control unit, and then they're showing. And by the way, I've had questions about this graphic because it looks like a finger, doesn't it? To me, that looks like, you know what I mean? It's got like the whole finger. That looks like a fingernail. I don't know.
Yeah, I kind of can't unsee that finger now.
Yeah, but what
Permanent
was it?
finger.
But what was it before I made it a permanent finger in your mind?
I don't know. It's the program counter, right?
It's the program, yeah, right? I mean, is it like point to the next instruction? Is that what it's trying? I'm not sure. And the other problem I have with IR is for me, because I worked in infrared, that can't be anything other than infrared. So I can't unsee infrared, but it is instruction register. So the two specialized registers. So it's a view. It's just a view into the von Neumann architecture from the book's perspective. Nothing great, you know what I mean? Nothing dramatic or not about that. So then this becomes really the punchline. The LC3 is it's an example of a von Neumann architecture. It's really simplified compared to kind of real machines, you know. And what I did kind of right here on this, I kind of grabbed this from the book, and there's just a number of things. I want to see where we go. Yeah, so what I'm going to do is kind of like walk around the neighborhood here and point out, the areas in our little city or in our little neighborhood. The big advantage to the LC3 is that it is so simplified. It really is a decent teaching tool, and so and it's really simple. It is. And what's interesting is like when we start looking at, remember when we talked about state machines and I had that talking about the state diagram, from the LC3, and you look at that and you're like, well, that seems pretty complex. Based upon anything real, it's not. But based upon you've never seen a state machine before, it's pretty big. And so I kind of feel the same way about this. The other thing too is that since the LC3 really kind of lives as a simulator, more than anything, one of the consequences of that is some of this is sort of like idealized. Okay, there's not like an actual chip and the LC3. Maybe someone's built it, but I don't think so. Or if there is, I don't know about it. First, that doesn't mean it doesn't exist. But so there's still like the idealized notion, and then you create a simulator that acts like all of this. Does that make sense? It's not really. I guess you could do a thing where you're like, and now I will take the something or other onto the bus, and I suppose you could break it down like that. But I don't know that the simulators and stuff do anything like that. I think it's an idealization or conceptualization without that level of detail in like an actual implementation. That's my sense. So anyway, let's kind of whip around the neighborhood. So there's memory, all the memory stuff, and we're going to break this all the way down. We'll drop all the way in to this memory stuff here, okay? So that's memory. And in fact, I guess the way I've got this organized, it's been a while since I've touched these slides, right? It's been I don't know how long it's been, at least a month. So I guess we're going to go ahead and like pick one and then drill down. But I probably would have preferred to bop around the neighborhood more first. But anyway, there's the memory. Let's drop in. So we kind of blow that up a little bit. We already know what memory is, right? And this is all that memory. And by the way, since we just barely talked about, memory mapped I/O, this memory with 16 bits in the MAR, so that there's the MAR with 2 to the 16th memory locations. Just understand that after, what did we say? FE00 was FE0? I think FE00 was where the memory mapped I/O locations began in the LC3. I'm just going off memory, but I think that's right. So in the memory locations from 0000 up to just shy of FE00, which would be FDFF, those locations are tangibly right in this memory, okay? But what's not drawn here is that all the memory locations that are the memory mapped ones, the MAR actually goes, it's not in this picture. It actually activates some other stuff, which we'll get to next lecture on the memory mapped I/O. In fact, I want to look. Yeah, it's not even there, but there's another diagram I have that has that in it. Okay. Relevant things. The MAR is 16 bits. The bus is 16 bits, right? Everything's 16 bits. So, and then this notation, the little slash, that little slash says that that represents 16 parallel bits coming in parallel, okay? 16 over here, 16 going out, 16 coming in, all right? And that's the MAR, which is the memory address register, which we dealt with in, I can't, temporal order, I can't remember whether we hit any, whether that stuff comes after this. No, it comes before. It comes before. I think. I don't remember. Do you remember, Ryan? I really don't remember.
Uh, a couple slides before this, we talked about memory.
But did we introduce memory in like chapter 3? I don't. Maybe we didn't.
I feel like I understand memory, so it must be something that I've covered.
Yeah, I'm not sure
But
because the problem is we're like in module 10 in real time, and we're
yeah,
doubling back because this isn't there for review. But normally we would hit these things, and it's like it's your very first time seeing it before you have all the other stuff. So it's really difficult for me to like tease that apart. But I'll do my best. Anyway, the MAR is the memory address register. It has 16 bits. That is the thing that tells us what's the spot in memory, right? It's like this decoder that just turns on one of those lines, okay? And so 16 bits gives us 2 to the 16th locations. The MDR is the memory data register. That's the one that the data's coming out or the data's going in, okay? All right, thanks, Sam. Sam, you can jump on the Discord chat too if you wanna, you know, just chime in. Okay, so the MDR is just where the data's coming in and out, and the MDR has to be the same size as one of the spots in memory. That's the rule of the MDR, right? And as we talked about, I think previously, the 16-bit addressable memory means that every location in memory has 16 bits in it, 2 bytes. So if I tell you there are 2 to the 16th memory locations, and I ask you how many bytes of memory are there, how much RAM is there, it's twice that. So it's 2 to the 17th actual bytes. Okay. Let's see, which would be what, 128 K? Is that right? What's 2 to the 16th? 2 to the 10th is 1,000, you know, 1K, 1,024. And 2 to the 6th is 64. So there are 64,000 approximately memory locations. So there's 128K of RAM in this machine, which is also microscopic by any kind of modern or real standard, right? Okay, so stop me. I'm just going to keep going, okay? Stop me if I need to pull back. Then we've got the input-output stuff, right? And interestingly, way back there in chapter 4, we were showing there's the data register, right? The keyboard data register, the status register. Oh, the D stands for display data register, display status register. That's it. And then we've now, right, more in chapter 8. What are we talking about right now? Chapter 8 in real time. So there they are. That's all. That's really all this is meant to be, is like a little teaser, point you out there for the future. Easy. Okay, now comes the processing unit. And I think I've apologized a few times for this pink overlay. This is just material from the book. And it kind of, the graphics that I have come like that. And my alternative would be either playing some Photoshop game to get rid of the color or recreating the thing from scratch. I'd rather not do that. Okay, so what's over here in the processing unit? Some of this I need to actually look over here, but these are the registers that we call the register file, right? This is register 0 through register 7. And the rest of this we don't need to get too deep into, but there are other little indicators, things that are like see that right, ld.reg. That's like an instruction into the register to load a register from some location. Obviously, it's like where is it coming from, and it's mysterious. And the DR is the destination register, and the SR are the source registers. And notice that that's 3 bits, 3 bits, 3 bits. So where that's coming from is there's no wires to show you, but it's actually coming from this instruction register, right? When you pulled an instruction out of memory, you put it in the instruction register, right? And the first 4 bits are the opcode, right? Well, those 4 bits, well, all 16 of these go piling into the finite state machine, as you can see right there. Well, 4 of those are driving the behavior that's literally driving the state machine. The next 3 are, going to be over here as the destination register. The next 3, depending upon the instruction, are over here as a source register, etc. Okay. So again, it's just trying to orient you to this idea. So things that are in the processing unit is an ALU. So that's I focused up here on this registers, but it's also the ALU for all the math stuff. Okay, this right here, this SR2 mux, we'll get a little more into it. But what you have is one line coming from the finite state machine, and then you've got. Here's the deal. Sometimes the value you're adding is coming from like the PC plus something or other kinds of stuff. So there's different ways of getting values into the ALU. Commonly, there's a source register 1 and a source register 2. Like when you do like an add instruction, right? And the opcode is 0001. And then you've got a destination register, then a source register, and then there's that bit, right? And see if I've got this right. If the bit is on, you have a literal value. Do I have that right? And if the bit is off, then you have a second source register. I think that's how that is. And if it's not, it's the opposite. That's when the second register.
I think it's the opposite.
Did I get it exactly wrong? Okay. Well, so somebody look it up because I don't remember. But the point just being that in one of the options, you have a second source register. So that's just like, there's the first source register, and then here's the second source register. But sometimes you're not getting that operand from a source register, you're getting it from somewhere else. That's what this multiplexer is about. Which, I've got possible values, which one is the one I'm using? That's what that multiplexer is all about. Anyway, we got the registers, right? Everything's 2's complement as far as math is concerned. If we're doing math, it's 2's complement. We've got bitwise and bitwise not, and that's all we got. No or, no sub, no mul, no happiness. All right, then comes the control unit, which is this bad boy right here, which has the program counter up there, the instruction register right here. This PC mux, this one is a multiplexer whose job is basically to decide what's going to go into the PC next. Okay? So what you can kind of see is one value actually comes out of a register because some instructions actually load the PC from a register, right? Sometimes it's just we incremented it, and sometimes it's the byproduct of some other, branch instruction where you've got a PC offset, right? So this just represents the fact that you've got multiple things. The PC might come from a couple of different sources inside the hardware. The easiest is basically just to conceptualize. One option is we just increment it, and the other option is, which is that one, and the other option is we just overwrite it with some other value coming from somewhere where we did some calculation. So that's it. The finite state machine, instruction register, program counter. Now, some people will take like all of that pink and kind of like call that the CPU. Totally fine. The lines, in my experience, the lines are a little bit fuzzy about what's what. So I don't really care, other than that generally that there is this notion of a CPU, that the ALU, there always has to be a little math guy. The control unit always has some kind of a state machine that's going to drive the behavior. There's always got to be some registers, general purpose registers. There needs to be a program counter, and some people even call that different things. There needs to be an instruction register, and folks will call that different things, okay? But that whole thing is like the brains of the operation, okay? All surrounded by a delicious thick crust of bus, right? And the bus, if you recall, is kind of how everything moves around outside of the CPU, how stuff's moving around. Cool. Notice we're not that far off of slide number 45. So now we get into how do we actually process instructions. Okay. So one of the big deliverables of von Neumann was this notion that you could put memory, that you could put instructions and data and just put them both in memory. The notion of historically the programming was done, you'd wire it up, you'd hardwire the program. Remember some of the early pictures we showed, right, when we introduced, some of these, there's like whatever, the ladies with the patch cables, and you'd plug things to create connections. Essentially, it was like you were like just rewiring the circuitry to make the new program, right? It was almost like you have patch cables. So instead of that guy going there, he's now going here. That guy's going there. And I'm like dynamically reconfiguring the machine itself. Von Neumann was like, one of the big genius things about it was I could basically just take memory. Here comes memory. I'm just going to put my programs right into memory with everything else. And then I've got that what they call what do they call it? Like a stored memory program. And then I can set a program counter that just basically says fetch, decode, execute. Fetch, decode, execute. And run a program. And that now you've just introduced machine code, right? Machine instructions. You've got to have memory. You can store bits in memory, pull the bits into another bit of memory that we call an instruction register, and then build circuitry that's generic circuitry, where what changes is what's in memory. You just got to understand how radical that was as an idea. When previously it was like every program was like reconfiguring the entire machine. And now I could run my computation because I had a brand new machine, and I unplug all the cables and replug it in. You know what I mean? Just think about like those, like the transistor circuits and stuff like that. Just think of that. Only it's all big and it's all wires to connect stuff. And now I do this, and I've got an AND gate, and I do that, and I like, all that kind of almost like circuitry level programming. And all of a sudden I had one machine, and I could write different programs just by putting that bit pattern in memory. It's a radical idea at the time. It makes total sense now, but man, when you understand where it was coming from, it was pretty incredible. So that was a big takeaway. And then the notion of the fetch, decode, execute cycle. That, to me, that was like the powerful deliverable of von Neumann. Okay. So here's the instruction. Now, the funny thing again, Ryan, like we were talking about, it's like, I think I know some of this by now. So yeah, this is one of those that we kind of really know by now, if you're just sort of still in the class, right? Is that there's this notion of an instruction. An instruction is a chunk of a program that is occupying a single word in memory. Okay? We call that an instruction. When we do the fetch, decode, execute, the thing we're fetching is an instruction. The instruction has, broadly speaking, two chunks. The first is the opcode, right there, which is in the LC3, it's 4 bits. In every other computer in the world, pretty much, it's more than 4. Okay? But in the LC3, it's 4 bits. Everything else, it's called operand fields, but it really just means like everything else. And everything else is conditional upon what the opcode is. Right? You give me 4 bits, I'll give you 16 possible opcodes. Give me 5, I'll give you 32 possibles. Give me 6, right? I'll give you 64 possible opcodes. So that's it. In this case, each instruction is 16 bits because it just occupies one spot in memory, and every opcode is 4 bits. That's really all this slide's trying to just introduce you to that idea. And this is what I was just talking about. How many opcodes are there? Well, there's a maximum of 16. And by the way, I'm also lumping together, like, we talked about you flip that 1 bit for an add or an and to get a literal value versus a second register, a second source register. I'm counting those still as one opcode. That it's both of those are like an add or an and. It's still just that opcode. How you treat it is conditional. Cool. All right, so then here's an example. I was right. Write it down. Props to Dr. K. I got one right. I'm not rewriting history, am I, Ryan? I think I said that if the bit was on, that you got the immediate, and that if that 5th bit was off, you got a second register. It's recorded. We can go back and check. What do you think? Wait, hang on a second. I'll bet we're at that point where I can't hear you. Just a second. Okay, I'm back.
Hello?
Yep. No, this stinking Discord does this thing where just periodically I can't hear. It just cuts out, and then I just can't hear any of the voice channel stuff.
I see.
Yeah. No, anyway. So yeah, no. Are we confirming that I was correct?
I still think I think you said the other way, but it's not a big deal really. Either way.
No, I need to win.
Okay.
I don't really need to win. But I was
after this, I'll go back and check. Okay.
Yeah. I'll buy drinks. I'll buy Diet DP for you and the 2 Williams if I was wrong. No, anyway,
right.
It was more. It's more, you get just kind of like something to keep it interesting. So okay, yeah. So here comes the add instruction, and then this notation, which can be a little bit confusing, is like bits 15 through 12 or 12 through 15 if you want to say it that way, right? That's the opcode. These bits 11 through 9 or 9 through 11 is always the destination. Well, it's whenever there is a destination register, that's where it is. And whenever there's a source register, at least one, that's where it is, right there. So that's it, source register 1. And then the idea here is that these 3 bits identify the register. So 000 is register 0 and 111 is register 7. So that's the multiplexer basically, or the decoder that goes, it's not a multiplexer, it's a decoder that goes into the register file and says, I'm talking about this one. Okay. And then on the add instruction, so what we were doing was we were using the add instruction as kind of like a case study to understand instructions. It wasn't so much about add as it was about instructions. And since it's super simple and it's not the most simple, but it's very common. Then comes this bit, which if it's a 1, we get an immediate value. If it's a 0, we get a second source register, as I said earlier. So, or not, one of the two, but certainly one of the two. And then comes, in the case of a second source register, 5 is 0. These guys are hard-coded to 0. And then comes these 3 bits for the second source register. And when bit number 5 is 1, we get a 5-bit immediate value. Oh, so tired. This is a 2's complement number, 5 bits. And this is key. This right here, only 5 bits, that's actually a key idea. Okay? It's only 5 bits, which means for this immediate, like I've got some register and I just want to add an immediate value, it's not much to work with, right? So I'm going to go for either Ryan or the Williams. This is interactive time. What's my range of values? I got a 2's complement number that's 5 bits. What's the range? What's the up or down?
Could be -16 to +15. Is that right?
2 thumbs way up. Yeah, that's right. That's right. You got +15 to -16. So this is really the key. So what I mostly see when you've got this kind of an add instruction, mostly what I see is, let's say I just want to move a value in the LC3 from this register to that register. Well, one way to move it, some architectures, most have like a move instruction that's like move this value from this register to that register, right? That's a thing. Well, in the LC3 you don't have that. So what can you do? One is I can take this register, add 0 to it, right, and put the result. And all that really does is take source register and puts it into destination register. Okay. I'm getting the scratch. I've been talking all day. So I apologize for that clackety clack that's now going to happen. I'll try to keep it down. So I can add 0, and in that instance, it actually makes sense. Another one is I'm doing like I'm incrementing through a list of things, right? I want to take some value and I want to just keep adding one every time for like a counter. I can do it that way. I want to subtract 1 every time. I want to add 2 every time I'm skipping through something. Or 4, or whatever it happens to be. Good thing we're about out of slides, because my voice is suddenly just like going completely south. Oh yeah, then we had a load register. Sorry, that's just probably, I bet that's horribly loud on the mic. I'm going to bet.
Like the eating of whatever
Just
you're
the
eating?
clacking. I'm just trying to suck on a cough drop, but it's like...
Honestly, it's not bad.
Really? And
I can't really hear it
It's
at all.
feeling like it's really clacky, you know what I mean? And I just don't want to broadcast the clack. Okay, so going back, the load register instruction, which we didn't go into it yet, and we're later on going to break down the load register instruction. But we just threw it here just as an example, like, well, that was add. Here's another instruction, okay? And like this is load R. So the whole point being, there's the opcode, it's different. It still has a destination register. Then it has a base register and an offset of 6 bits. And we'll get into like what we do with that, okay, in the later lectures when we break down all, because we go through all the instructions from start to finish. But just to kind of show you that there's a different layouts depending upon, what the opcode is. Boom. That had to be faster than, I don't even know what time it is.
It says you've been streaming for about 45 minutes.
Not too bad. Usually in a live class with 30 students, there's more questions, or you know what I mean.
Yeah.
You bog down a little bit. Um, yeah. So that's 17 to 45 from chapter 4, the missing lecture, and then I guess we've got all of what did we say? All of chapter 5, Ryan, and then
Yeah.
the first chunk of chapter 6. Um, I
Yeah.
can't remember
Yeah.
exactly, but
Pages 1 through 42 of chapter 6.
1 through 42. Okay. Yep. Anyway, so that's it. That do you have any? One of the Williams already bailed, and we've got like 5 concurrent viewers still. I hope. I know I got Sam over on YouTube. Um, I hope that's valuable as a backfill.
I think so.
And the other thing what I really want to do, Ryan, is, and I'll get to it, is go back through. I mean, there's still like the in-class experience, which I think is really valuable for the interactive thing. But what I really want to do is create kind of help materials that are much more canned. You know what I mean? Like more like 10-minute YouTube videos about
I
the thing.
gotcha.
You know what I mean? And then you kind of hit the
Yeah.
channel, and it's like, here's the playlist for. Here's the chapter 4 playlist. Here's the chapter 3 playlist, and it's multiple, and you can kind of reinforce the part you don't, that you're missing or whatever. That's
Yeah.
what I'd like to do. In the mythical future, when all things are possible, is when I'm going to do that. So that's it. Do you have any lingering questions at all on that?
None that I can think of.
Okay. Alrighty. So that's good. I'm gonna stop the streaming on this one, and then let's brainstorm a little bit about, when we can do the other ones, because I don't know how many days we normally did chapter 5, but I wouldn't be shocked if that's a couple hours to work through. So we can either do it in one shot and then it's just out there, or we can break it up. But we can break it down. So I'm gonna go ahead and just kill the stream on this, and then just let's just stay on chat for a second for whoever's on Discord. We can talk about it.
Sounds good.
All right.